So we're going to spend another day on inscribed angles, but we're just going to add a couple of theorems, additional theorems here. So if you remember from the other day, an inscribed angle is where the vertex is on the circle. So this here would be an example of an inscribed angle. And some of the things about an inscribed angle, one thing is that the measure of an inscribed angle is half the measure of the intercepted arc. So for example, if this was 60 degrees, then this inscribed angle would be 30 degrees. Another thing is two inscribed angles that intercept the same arc have to be congruent. That should make sense because they both would intercept 60 degrees. So for example, the red angle and the black angle are going to be congruent. They're both going to be 30 degrees because they both intercept the same exact arc. And then this other thing we're going to talk about today, this is the third thing we'll look at. Parallel chords intercept arcs that are equal in measure. And I think that'll make more sense when we look at an example here. So it actually happens to come up in our very first example. They tell us AB and CD are parallel. So we know those two angles are, those two segments are parallel, AB and CD. Then they tell us that ADC is 42 degrees. We want to find out the measure of arc AB up here. Okay, so I'm going to label that as X. All right, so what we need to do is try to find the measure of, we need to find, oh, they also told us here, so I knew I was missing something. And the measure of CD is twice the measure of AB. So CD is twice the measure of AB, so I'm going to label this as 2x. Okay, we want to try to fill in all of our possible arcs. So we labeled this one as x, we labeled this as 2x. We have an inscribed angle here. So ADC is an inscribed angle. Since ADC is an inscribed angle, we know our rule for an inscribed angle is that it is half of the intercepted arc. So the intercepted arc is AC. If the angle is 42, then the arc has to be 84. Okay, we could fill out this last arc BD, and that has to do with 3 right here. Parallel chords intercept arcs that are equal in measure. So both AB and CD, so AB and CD that are in yellow, they intercept AC and BD. Arc AC and arc BD. Those two arcs have to be congruent. It's just kind of one of our rules here. So this is also 84. So we actually labeled every single arc. Every single arc has something on there. This is X, this is 84, this is 2X, this is 84. If we want to think about it, a full circle is 360 degrees, so we can come up with an equation. We could say X plus 84 plus 84 plus 2x has to equal 360 degrees. Now we have an equation that we could solve. So I can combine like terms. 3x plus 168 equals 360. Subtract 168 from both sides. Just 168. 360 minus 168 is 192, and then we'll have to divide that by 3 to get 64. So this was 3x equals 192, divide by 3, x equals 64. And that is the measure of arc AB. So the measure of arc AB equals 64. So you can see it's starting to get a little bit more complicated. You have to think about some things here. Take a look at this next one. In the diagram below of circle O, BC is a diameter. That's important. OA is a radius. DC is just a chord. If you remember from the other video, a chord just goes from endpoint to endpoint. And then they also tell us that DC is parallel to AB. So I'll do the parallel symbol. So this little arrow here just to indicate that they're parallel. if BCD is 30 degrees, determine and state the measure of AOB. Call this X. Okay, so there's a couple of ways you could think about this. First off, we could say, all right, well, this is an inscribed angle, it's 30 degrees, so then this here is going to be 60. Then we could say, well, DC and BA are parallel, so DC and BA are parallel, which means that if this arc DB is 60, then this arc CA is also 60. Okay, so we have two arcs here. This is a diameter. Think about what a diameter does to a circle. It cuts it in half. So this side is 180, and this side over here is 180. So I could label this as 120. Well, if this arc is 120, BOA is an inscribed angle. Is a central angle. This is a central angle, so it's equal to the measure of the arc it intercepts. So it intercepts this 120 degrees, so AOB has to be 120 degrees. There's some other ways you could think about it. I'm not going to go through all of them, but I'm sure you can get creative and find other ways. So moving on, we're going to take a look at inscribed angles in semicircles. Semicircle is just half of a circle. The first question says to explain why BEC. So BEC, why is BEC, BFC, BFC, and BDC, I'll do that in yellow, BDC, why are all of these congruent? Why are they all congruent? Well, let's think about what they intercept. We could easily say that these two are congruent because they intercept the same arc. They're both inscribed angles, and they both intercept the same arc. They both intercept arc BDC going this way. Inscribed angle BDC intercepts arc BEFC, but think about what these arcs are. Both of these arcs have to be 180 degrees. So we could say angle BEC, angle BFC, and angle BDC are inscribed angles, that intercept a semicircle. They all intercept the semicircle, which is 180 degrees. So if they all intercept 180 degrees, they all happen to be right angles, because inscribed angle is half of the arc. Okay? An explanation would just be an inscribed angle is half the measure of the arc. If the radius of circle A has a length of 5 inches and BD is equal to 6, determine the length of DC. I'm going to call this X. So the radius is 5. So from A to B is 5, and from A to C is 5. So this whole thing here would be 10. We actually have a right triangle going on here. So maybe I'll just redraw it and pull it out. Well, I could do it with, I could add another side here. So I'm going to go ahead and pull this triangle out. Okay, so we have this yellow triangle. Maybe I'll make it a different color now, make it blue. Easier to see. So we have this triangle here, it's a right triangle. I know it's a right triangle because this is an inscribed angle that intercepts a semicircle, so right angle. This is 6, this is 10, and this is X. So think about how we find the missing side in a right triangle. So how do we find the missing side in a right triangle? Well, we would use the Pythagorean theorem. So we can go ahead and use the Pythagorean theorem, a squared plus b squared equals c squared. We don't necessarily have to here. because this is what we call a Pythagorean triple. It's a 6, 8, 10 right triangle, but we certainly could have, have done this, did it all the way through. We'd wind up getting x is equal to 8. Okay, we use our property of right triangles. Since it's a right triangle, we can use our Pythagorean theorem. So moving on, inscribed angles in a semicircle are pretty important because they do create right triangles. And we know right triangles, we can use the Pythagorean theorem. Right triangles, we could also use something else, which we'll see here. So they tell us OC is 8. O to C is a radius. So OC is 8. Well, that also means that OA is 8. All radii are equal. So this whole thing is 16. AB is 5. Find the measure of angle BC to the nearest degree. Find the measure of arc BC to the nearest degree. So this arc right here. Okay, let's think about this. This is a right triangle because angle B is inscribed in a semicircle. Here's our semicircle. AC is a diameter. AC cuts it in half. So arc AC has to be 180 degrees, which makes this 90 degrees. We want to find the measure of arc BC. Okay. If we want to find the measure of arc BC, then what we really want to do is find the measure of angle A. The reason why we want to find the measure of angle A is because angle A is an inscribed angle, which means that it's going to be half of whatever this arc is. So if we could find this angle, then we'll just double it and we can get the arc. We have a right triangle. We have a right triangle and we have two sides. We have two sides in our right triangle and we want to find an angle. Think about last unit, how we can go about doing that. If we have two sides and we want to find an angle, and it's a right triangle, what can we do? Well, we can use right triangle trig. We can use SOHCAHTOA. So we're trying to solve for this angle here. We have a hypotenuse, we have an opposite side, and we have an adjacent side. We're going to use trigonometry, and we'll specifically use cosine. So we could say cosine of angle A. So cosine of angle A equals adjacent over hypotenuse. We're going to have to use inverse trig. So this is from last unit. Everything always comes back to go ahead and solve for that angle. So we'll go over to the calculator. Okay, make sure you're in degree mode. I've been kind of working back and forth with Algebra 2. So in geometry, we want to be in degree mode. Second cosine, 5/16, and then hit enter. So we get 71.79 is the measure of the angle. So angle A is 71.79 ... Now the arc is going to be double that. So we have to take this and double it. So to the nearest degree, it's going to be 144 degrees. 144 degrees. So the measure of arc BC is 144 degrees. And that was a tough one. Okay, moving on, a couple more practice ones. This one's pretty straightforward. This was a Regents question. It's just really knowing vocabulary. So it says that we have this guy Sam, and he says the most important thing here is that he states an angle inscribed in a semicircle is a right angle. They give us a couple of things here. They just give us line segments. We have circle O. We'll learn about what tangent means. Something different, not the trig tangent. But he says, an angle inscribed in a semicircle is a right angle. Which angle is he referring to? Okay, so we're looking for an inscribed angle, So let's just go through our choices. AOB. Is AOB an inscribed angle in a semicircle? No, it's a central angle, so that's out. BAC. BAC. So that's inscribing this angle. No, that's not a semicircle. I'm gonna highlight this diameter. Here's the diameter. They tell us that in the question. That's important. That yeah, because it goes through the center, so that's your diameter. So let's keep looking. You may have found it already. DCB. DCB. Yeah, that looks good. Because this is an inscribed angle. It's on the circle, so it's inscribed, and it intercepts this arc going all the way around here, and that happens to be a semicircle. So DCB is your answer. Okay, FDB. FDB is not an inscribed angle because this kind of goes off. It is a right angle, but it's not. That's not an inscribed angle. It's not the definition of an inscribed angle. Okay, I'm going to skip this one just for some time's sake here. Okay, and then here's the last thing we're going to take a look at. It's called, it has to deal again with inscribed angles. And it's a special type of quadrilateral known as a cyclic quadrilateral. It's a quadrilateral where all of the vertices lie on a single circle. So on the circle, on the circle, on the circle, and on the circle. So it creates a quadrilateral if we connect all the points. And it says, what is the relationship between the opposite angles? So let's take a look at our opposite angles. So angle A and angle C are opposite angles. Angle D and angle B are opposite angles. So we want to know the relationship between them. You could probably see that they add up to 180 degrees, so they are supplementary. Okay. Opposite angles in this type of quadrilateral, and inscribed, this quadrilateral is inscribed inside the circle, opposite angles are supplementary. And they ask, why is that true? Well, let's just kind of take a look at the red ones for a moment. Okay, let's take a look at these red angles for a moment. So angle A is an inscribed angle, and it intercepts this arc here. So it intercepts this arc here. Angle C is an inscribed angle, but angle C intercepts this arc. Well, those two angles added together intercept the entire circle. They intercept 360 degrees. So together, added together, the angles are going to be half of 360, which is 180 degrees. So I don't know, we could say something like opposite angles intercept the entire circle, which is 360 degrees. Inscribed angles are half of the intercepted arc. So that's going to be half of 360, which is going to give you the 180 degrees. So these opposite angles, they're going to intercept the entire circle. We could see angle A intercepts the blue arc. Angle C intercepts the green arc. That winds up being the entire circle. So half of 360 is 180. Just take a look at one last question dealing with this. So we have quadrilateral Q, R, S, and T is inscribed in the circle. So all of our vertices are on the circle. This is inscribed inside. So it's a cyclic quadrilateral. the measure of QRS is 12 degrees less than 3 times the measure of QTS. So I could say QTS is X, and QRS is 12 degrees less than 3 times that. So 3x minus 12 is the measure of QRS. Determine the measure of QTS. All right, well, these two angles are going to add up to 180 degrees together. Okay, so we're going to say x plus 3x minus 12 equals 180 degrees. If we look back here, they're opposite angles. We know opposite angles will always add up to 360 degrees. These are opposite angles, so they're going to add up to, 180 degrees. So we can solve it out. 4x equals 192, and divide by 4. So what is that? 48. Let me just check that. 192 divided by 4. Yes, 48. Okay, so QTS is equal to 48 degrees. So what is the common measure of RQT and RST? I'm not sure what that's really asking. I think we're just going to say the measure of RQT plus the measure of RST has to equal 180 degrees. So we'll just say something like that. Okay? All right, so we'll end here, and that's it. Have a good day. Bye.